So I'm Valeri Slavchev, and I'm going to talk about generation of vortex structures in optical fibers with spatial dependence of linear and nonlinear refractive index. So first, I will introduce some words about the optical vortices. So actually, the optical vortex is referred to a beam or pulse that has a singularity in the amplitude phase. So the last one is characterized by helical phase front. These vortices admit only amplitude-type singularities, and their stability is a result of the balance between diffraction and non-linearity, as well as non-linearity and island distribution. So also these light structures are a solution of two-dimensional paraxial scalar equation of Leontovich. They are usually created outside the laser cavity by using optical holograms or different optical masks. Their behavior of this type of vortices in different waveguides is described by nonlinear amplitude equation, in which it is included a term which corresponds to a spatial dependence of nonlinear refractive index from this type. So the amplitude modulation in such optical structures are observed in the case of studying of the vector structure of electrical field, and they are investigated in the frames of two scalar nonlinear amplitude equations for the components of a vector electrical field, x and y. It is also taken into account the effects of second order dispersion and cell phase modulation. Also can say something specific about these optical vortices. They have a number of applications in the field of high resolution microscopy, optical tweezers, quantum information transfer, optical vortex trapping, and many others. For all investigation, we use equation 1, which equation describes the propagation of optical vortices in waveguide with spatial dependence of nonlinear refractive index, with A is right on the vector amplitude function of pulse envelope. Alpha is the constant correspond to the number of oscillations under pulse envelope. Beta is dispersion, and gamma is a nonlinearity of the fiber. With delta, we have right on the transverse operator of Laplace. These constants are presented in equation 2, where k0 is the wave number, z0 is initial longitudinal length, where u is the group velocity, k double prime is the second order of linear dispersion, and N2 is the nonlinear refractive index of the medium. We have in mind that the vector of amplitude function is in this kind, so that it's expected to that the axis OZ coincides with the geometrical axis of the fiber. So this will work in the cylindrical coordinates, which are written in equation 3. After a couple of transformations, the equation describing the evolution of the components of vector A, AX, and AY, written in polar coordinates, can be presented as following equation 4. In order to find solutions of these equations, we make the following substitution in the system 4 with equations. So here, Px and Py are new unknown functions, and in the equations, equation 5, A and B are constants. After a couple of transformation, we obtain equation 6, where you can see the left sides of these equations are the same constant expressions. Also, the right sides of the functions are variables of r and theta. So in order to fulfill these equalities, we assume that these constants in the left side will be equal to 0. From this equality, we find the connection between the constants. We're looking for about the A and B, right in equation A. So having in mind the expression 7, equation 6 take this form, and after another substitution, these real functions have these expressions in equation 10. By using the substitution of 10 in the system of equation 9, can be presented in this form, also taking into account of nonlinear terms in the equation 11, it's convenient to search for the solution of this kind, where B, mu, m, and eta are constant about to be defined. By substituting the expression 12 in the system of differential equation 11, and after short transformations, we obtain equation 13. So to fulfill these equalities in 13, it's needed that the coefficient in the front of the respective geometric functions in both equations are equal of 0. Thus, we obtain the following system of two ordinary differential equations. 14. So as you can see here, by using of the system of equations, we can define the constants mu, eta, and p. Thus, the following exact solutions describing the optical vortices propagating in the fiber with the spatial dependence of nonlinear refractive index are found. These two equations, after some substitution and assumption which actually made by now, we can come back to see how they can be look like in the initial components of the vector field ax and ay, and we observe the results of the basic equation 1 right in 17, where m is in our case vortex parameter, which vortex parameter has the values equal of 1, 2, 3, and so on. After that, we made the graphics about our solutions. First, for vector parameter equal m equal of 1. In this graphics, you can see it in figure 1 and 2. We have optical structures which are specific for this kind of vortices, and they have ring structures, but they are obtained only in the components of vector amplitude function, as you can see, A and B. But in the total intensity profile, these optical structures disappear because there is superposition of the two components. After that, we made a vector diagram of all solutions, and we observe the rotation of the vector A in the center of the optical vortex, which is shown in figure 2. That's another specific, another characteristics of these structures, optical structure, that is the depolarization in the vector field. After that, for case m equals 2, we observe that the number of the rings decreases, and this leads to a narrowing of their minima and maxima. So that means these vortex parameter correspond very well to the number of the rings presented in the components of vector field. In the vector diagram for m equals 2, it's clearly seen that by decreasing of the vector parameter m leads to a significant change in the vorticity and depolarization in the vector diagram. So we can conclude that in this work, vortex solution for the components of ax and ay of the vector amplitude function are found. So the basic vector nonlinear amplitude equation is presented as a system of two scalar equations of the components of the amplitude function. The graphics of the obtained solutions for the different values of the vortex parameter are presented. The value of the parameter m determines the number of the rings observed in the profiles of intensity components. Other part of our investigation is about vortex structures which are observed in the fiber with concave gradient fiber. So actually depend on the refractive index. There are two types of gradient fibers, convex and concave gradient fibers, which are presented by the following expression, where N2 and N0 are linear and nonlinear refractive indexes characterizing dispersion nonlinearity of the media. Second expression in the equation is gives the spatial dependence of refractive index. So as you can see in the figure 1, this is a distribution of the refractive index of concave gradient fiber. What's specific here? The specific is that the refractive index of this kind of fiber is that the refractive index decreases toward the center of the fiber. So actually we're looking for the solution for this kind of fiber. So for that, we use the equation 1, which describes the propagation of pulse in this type of fiber. Write on the equation in this form, where SD and SG are constants, and we're looking for solutions for the vector amplitude function. The following, the same mathematical algorithm as the previous part, we following the exact solution of the system equations are obtained describing the formation of vortices in a concave gradient fiber. That's the equations in 2, where Ux and Uy are the components of the vector electrical field of the amplitude function. In this case, n is the vector parameter, which corresponds to angular distribution of the vector structure. And actually, to form the structure, needs the parameter have is this parameter to have the values 2, 3, 4, and so on. So on these graphics, we can see that the propagation of the laser pulse in this kind of optical fiber show that we receive different optical structures, which actually have helical structure, which is specific for concave gradient fiber. And again, these vortex structures exist only in the vector components Ux and Ui, and disappear then disappear in the total intensity profile. Also made the vector diagram for the found exact analytical solution, first for the case n equal 2. There also we have rotation of the polarization vector in the center of optical vortex. For the other case, when the vortex parameter n is equal to 3, it is presented again profiles of components x and y of the electrical field. Here, you can conclude that the significantly more intense vorticity at the higher value of the n is observed, and it's clear seen that the increasing the vortex parameter leads to a significant change in vorticity. Also, by taking in account the 2 branches of the helical structures in the components x and y of the vector field, it is observed that their number corresponds exactly to the parameter n. This is very specific about, and it's important about these results here. Comparing these results about the vector diagram with the vector diagram for n equal 2, we can conclude that for n equal 3, the level of depolarization is significantly greater. That's clearly seen in this figure 2. About the second part, we can conclude that the dynamics of propagation of the pulses in such fibers is governed by the scalar amplitude equation. So we generalize this equation to a vector system of equations for the components of amplitude envelope. Vortex solutions for the components of the electrical field that we found, we have a helical structures. The number of helices correspond to the vector parameter n. Specific characteristic of these vortices is that they exist in the frame of the vector components only. In the field of the total intensity as a result of the superposition of the 2 components, the helical structures disappear. To observe these vortices in the field, it's necessary one of the components to be filtered. The important effect of these amplitude vortex structures is that they generate depolarization in the vector field. That means in each point of the spot of the pulse, different orientation of the vector field is observed. So this work is supported by Bulgarian National Science Fund. And thank you for your attention.